and a warm welcome to this workshop. I hope that everyone is safe, everyone is healthy, and everyone is doing good. My name is Monalisa Chaudhary. I am basically from Assam. I have I'm a geologist. Basically, I've done my master's in geology, and then I was in IIRS ISRO, where I got a postgraduate diploma in remote sensing and GIS. Currently, I have been working as a freelancer for some time, and very soon, hopefully next month, I'll be joining as a remote sensing executive in a mining company in Mumbai. So this webinar is basically about remote sensing and GIS and how important it is in the field of geosciences. So we have got today and tomorrow, and basically in a 2-hour session, giving everyone a very thorough idea of the subject is not that possible. So what I have done is that I've tried to make it as compact but as precise as possible so that everyone can get a very good idea of what the subject is and how it is used as a tool in geosciences. I do not know how many students here are from geology, or are there any professionals from the same field, or if remote sensing professionals are listening to me today. But I've kept it in a very basic tone so that everyone, even if the students do not have any idea of remote sensing or and GIS, they will get a very clear idea about it. And today for this workshop, we will be discussing about remote sensing, and tomorrow we will be moving to GIS. Right. So I'll stop my video, and so that we can completely focus on the PowerPoint presentation on the screen. Okay. So let's begin. Just a second. Yeah. So what is remote sensing? Right. So basically, the word remote itself will give you a clear idea of it's about a tool or a scientific approach where we are using or we are obtaining information about objects or our surroundings from a distance. So basically collecting and analyzing information about any material from a distance without even touching it, that is called remote sensing. Now, this is a very important field, and this is a very necessary field, because sometimes, and most of the times, we cannot actually go to certain locations, especially if geology students are hearing me or geology professionals are hearing me. You know that in geology, we cannot go to different fields all the time. Not all the places are accessible to us. So that's where we use remote sensing to actually gather information regarding those places, those inaccessible areas as well. Now, this is a brief definition of remote sensing that I have put here from a book of written by Lillison. So, remote sensing is the science and art of obtaining information about any object, area, or phenomena through the analysis of data acquired by a device that is not in contact with the object, area, or phenomenon under investigation. Right. So now, since our birth, we've actually realized that remote sensing is like, what is it not, what is the science about it. But actually, we have been doing remote sensing since the moment we were born. Our eyes are the basic examples of how we remotely sense our surroundings around us. Right, you see things, you process them, you analyze those things, and that's how you gather information in your brain about your surroundings, and you reach to conclusions. So our eyes have been doing this remote sensing technique since for a very long time. We just don't realize it. Now, next, the science behind it. Right. Now, this is actually a picture that is very common. If you go to Google and if you search, remote sensing images or anything, this image is ought to come in your search engine. So here, what we are saying is that if you can see my cursor, now this is the sun. Now, we all know that in remote sensing, what are we actually studying? We study electromagnetic waves. Now, electromagnetic waves are, we are not going to, there has to be some source, right, for these waves. So basically what we do is that we have a sun, which is the source of illumination for us, as we all know. So from sun, every day, every moment, we are getting energy. Now, this energy actually hits every other material, every other object on earth. And when the rays of the sun are interacting with these objects, for example, they're interacting with trees, they're interacting with grass or buildings or paved roads, either it goes through one of those 3 or 4 processes. Either it goes through reflection or refraction or absorption or scattering. depending on the type of surface it's hitting. From there, for example, the ones that are the rays that are getting absorbed, that remains within the object itself, but the ones that get reflected back, those are actually captured by a satellite which is actually moving right. In fact, even right now some of the other satellites are actually rotating above our heads. So these rays are continuously being sensed by the satellites, and from there, and there the information regarding these particular objects are actually captured. So basically what we are doing is that the sun, we are actually calculating the energy of the sun which is hitting these particular objects around us, and we are capturing it in a satellite so that we can study it, analyze them, and in our computers sitting at home. Now the next slide. Now, yeah, this slide is actually telling you what happens after the information is gathered in a particular satellite. After that, the satellite actually transmits these all the data that it is gathering, and it is received by an antenna receiver which is on the ground on earth. And from there we get it in our computer so that we can analyze it according to our needs. Now, different fields have different needs. Sometimes we are using this satellite information to gather information about the weather forecasts. Some people like us geologists, we want to know about the lithology of a surface. We want to know which minerals are there in this particular place. We want to know if for example, if there is a burning coal mine underneath working. So whatever, according to our usage, according to our needs, we take this data and we analyze it based on that. Now here I would like to mention a very specific thing. See, when the rays from the earth, or let's say the electromagnetic radiation, to be very technical, the electromagnetic radiation from the sun, when it hits the earth, it actually passes through the atmosphere, right? So there in the atmosphere, it's even in the atmosphere, it's not blank, it's not a vacuum, right? Our atmosphere, we have so many particles, we have dust, we have smoke, we have an ozone layer surrounding us. So all these layers are actually interacting with the rays in their own sense. After that interaction, these rays are actually hitting our earth, and while the sensor is receiving these rays back from the earth's surface, these rays are again passing through the atmosphere. So what happens is that when the satellite, at the end of the day, when the satellite receives the data, we actually get a very raw, we call it level 1 or level 0 or raw data, which means it needs to be atmospherically corrected, because the atmosphere changes the data itself, or however the data is interacting, however the electromagnetic radiations are interacting with the molecules in the atmosphere. We need to make corrections in it so that we can actually get the perfect results, or we can get the corrected, atmospherically corrected data, so that we can start working on it. Similarly, like for example, that we have been talking about global warming and all, and we know that this ozone layer, actually what happens is that because of the depletion of the ozone layer, more of UV rays are coming to us, which is actually unhealthy for human beings. Why is that happening? Because actually the ozone layer absorbs the ultraviolet rays, and it does not allow the ultraviolet rays to reach the earth's surface. This is another reason why ultraviolet rays are actually not used to study any of the earth's objects, mostly according to my information, because all the ultraviolet rays are absorbed by the atmosphere. Now if you want to study atmosphere itself, if someone comes from meteorology department and they want to study the clouds, or the formation of the clouds, or weather forecasts, or anything related to the atmospheric phenomena occurring, they can study the ultraviolet rays. But because of these rays being absorbed by the atmosphere again and again, so we cannot study the earth features. Now there is another thing that I would like to mention here. There is a term called atmospheric windows in remote sensing. It's a very basic term. I am sure people who have read remote sensing, they must have known what it means. Uh, Atmospheric windows are actually just like, for example, let's say in your house you have a window, right? So what is the working of your window in your house? It lets the air come inside, or it allows the to and fro flowage of air in your home, so it feels good, right? So atmospheric windows in the atmosphere acts as similarly as the window in your home. It allows the electromagnetic radiation to enter the Earth's surface, hit the Earth features or surroundings around us, and then it allows the electromagnetic radiation to go back to the satellite so that it can be received by the satellite itself. So, for example, there are certain, we will come in the next slides about this in detail. We will read about it in detail. For example, there are certain wavelength, or there are certain ranges where you cannot actually get the information from the satellite. I'm sorry, you cannot get the information from the electromagnetic radiations coming from the sun, because you do not have the appropriate atmospheric window to it. Are you getting my point? Like the atmosphere, if the window is closed, the air will not be allowed to come inside your room, right? So there are certain blockages in the atmosphere where it does not allow certain spectra or certain wavelengths to enter the Earth's atmosphere. So we cannot study the Earth features using those gaps. So whatever we study, whatever we know about remote sensing, whatever analysis we make is absolutely completely based on the wavelengths or the electromagnetic radiation having a certain specific wavelengths which can come through the atmospheric windows. Sorry. Yeah, so next slide is about factors which are coming in to view while remote sensing process. This is basically what I've just said, but I'll be describing it in more details. Like for first, for any remote sensing process to work, you need an energy source of illumination. What are you going to measure if you do not have any energy source around you? You are measuring the energy, right? The energy that is interacting with the objects that you want to study particularly. So you need energy source or illumination. Now, why have I said here energy source or illumination? In the previous two images, I showed you how sun provide us electromagnetic radiation on a daily basis. Now, the thing is, the sun stays with us for around what, say, like let's say approximately for like about 10, 11 hours, or let's say about 12 hours. But what about the night time? The sun is not there, which means the illumination or the electromagnetic radiations from the sun is not there. We do not have that appropriate illumination. So what happens is that if you want to study a certain object during the night time, like for example, there is any disaster management person wants to study the abrupt changes that are occurring due to a flood going on, or let's say there is a cyclone in Orissa, and you want to see time and again the changes that are occurring on the coastal regions of Orissa. You cannot be dependent on the particular day itself, right? You need the night data as well. For many other fields of study, you need the night data as well. So what happens is that we actually provide artificial energy source. Some satellites are there. We'll come to it later on where we are talking about passive and active remote sensing. But let me just say it here in a very brief way that some satellites, what they have is that they have their own energy source that they provide, so that they can actually, when the sun is not there, when we are not measuring the sun's electromagnetic radiation, these satellites provide their own energy source which actually interact with the Earth's objects or whatever you are going to study, and they reflect back and they study that particular energy. Now, the next is that radiation and atmosphere. As I said, that the radiation has to go through the atmosphere to reach to the objects and then travel again back through the atmosphere to reach the sensor. So that is a two-way thing. Two times the radiation interacts with the atmosphere. So here the role of the atmosphere is very, very, very important. Uh, there are many other aspects to this. If I keep on discussing, it will become a very long conversation, but let me just say it to you in a very brief way. When we are talking about atmosphere, like as I said, there are various types of molecules that are present in the atmosphere. Depending on that, when the radiation interacts with these particular molecules, scattering happens. Now these scatterings can be of three types. One is called your Rayleigh scattering, one is called your Mie scattering, and the other term is non-selective scattering. Now, in these three scatterings, what happens is that the scatterings are mainly dependent on the size of the molecules present in the atmosphere. The Rayleigh scattering is due to the small air molecules, and the Mie scattering is due to dust, haze, and non-selective scattering happens due to the larger molecules like water vapor and water molecules in the atmosphere. Now, the reason why you see during the sunset the sky is red, and the reason why you see during in the morning that the sky is blue is actually due to your Rayleigh scattering. When the rays interact with the atmosphere, they scatter and they reflect the blue light, and that's the reflection of the blue light that we see. That's why the sky appears blue to us. Now, next is the interaction with the target. Right. So, as I said, the electromagnetic radiation is coming from the sun, or let's say from an energy source. Now, when I talk about electromagnetic radiation, we will come in the next, I think it will come in the next slide when I will talk in more detail about electromagnetic radiation. But there are different types of rays. In the radiation does not say that it has only one kind of a ray, in it. So different kind of rays has different kind of interaction with the target whatever you are trying to hit, whether let's say you want to measure the emission from a building, or let's say you want to let's just say that you want to see if a vegetation, suppose a vegetation is healthy or not, let's just say that. So for example, this infrared light, there is something called infrared rays, right? So when those rays are hitting a particular vegetation and they're getting reflected back. Now, what happens is that in a particular plant which has got a lot of more chlorophyll, like in a healthy vegetation, you will expect, right, that you will have a lot of chlorophyll than an unhealthy vegetation. So, in the healthy vegetation, if you have a lot of chlorophyll, a more amount of infrared rays are reflected. So what will happen is that when you will get an image in front of you, when from the sensor you are doing the analyzing in your computers, when you have an image in front of you will see that due to the infrared rays, because of the more amount of reflection of the infrared rays, a particular amount of vegetation is looking, much more brighter with respect to other vegetations. What it means is that this vegetation is actually has more chlorophyll, it's more healthy than the other kind of vegetation which is showing a less, a less brighter, or let's say a duller appearance. So that's how different targets interact with the different kinds of electromagnetic waves, and we studied according to our usage. We take these considerations depending on what we actually want to study. Next, we have recording of the energy by the sensor, right? So when the energy is received by the sensor, it is actually recorded in the sensor so that later on it can be processed. So as I said, you get the raw data is recorded by the sensor. Also, there are various types of process how a sensor records the energy. I can discuss about it. Actually, we are going to have a 3-week detailed workshop on this particular topic, probably in next month. So there I'll be discussing in more detail, in more technical way, like how a sensor actually records the energy when an electromagnetic wave is received by it. There are different ways of sensors doing it. Sometimes what happens is that, now sensors are what? Basically, these are instruments inside a satellite. So if we want to have more information about a particular area, what happens is that we have a satellite in the space. Now, there are a lot of sensors within that satellite. So sometimes what happens is that if we have a dual satellite, there are dual satellites, or there are single satellites. These satellites are taking information from the earth. Now there are multiple things that come into account here, like what amount of area are you covering at a certain specific amount of time. Like for example, right above your head there is a satellite moving above your head right now, and it is gathering information. What area is it going to cover? Do you think that it will cover the entire earth's the entire land in the earth? No, it won't be possible. We call it swath. There is a certain path and there is a width to that path, attached to that path, based on which the satellite is studying the features underneath it. Then there are another processes where how the sensors are recording their energy. One is called waveform, one is called push broom techniques, where it depends on how the sensor is moving within the satellite to capture the data. Next, we have the transmission, reception, and processing. Right. So when the sensor has received the energy according to whatever technique or whatever the specifications of a particular sensor are, it will gather it, it will store it, and then it will transmit it to the antenna, as I have shown you in the previous slide. And then you will receive the data from the sensor and you will start processing. Now, why processing is necessary? Like, why don't we just get whatever data the sensor has taken and just utilize it? What the satellite is taking is actually just energy, interactions of the objects with the energy from the sun or any other source. But what you want to do with this particular data is up to you, right? You can actually, for example, you see Google Earth. So what is Google Earth Maps? Google Earth Maps is nothing. It's using a particular satellite called Landsat 8. It's a sensor, and they are taking images from it, and you can see Google Maps. Now, there are so many people right now in our industry, and the usage of Google Maps is so different to different people. You want to find the nearest restaurant nearby, you are using Google Maps. You want to see which are the trekking locations around you, you are using Google Maps. You want to measure a distance between you and your, let's say, in terms of geology, you want to go to a field, you want to see which directions you want to take, what you want to do, you are using Google Maps. Let's say, for example, I have a company and I'm trying to build a dam. So when we are building engineering structures for like dam and tunnels, so we ought to make sure that our construction site is very, very nearby to the raw materials from where we are going to gather it, because otherwise then the economic cost of that is going to rise. So what you do is you just open Google Maps, or you see, okay, do I have like any industries nearby, do I have raw materials nearby, how much further is the nearest village from here, or the town is from here, so that my workers can go to and fro. So the different people, the usage is different. So that's why the processing is very important, because in processing you are not only dealing with the atmospheric processing, or you're not only making the data correct, but you're also analyzing it, you're also gathering information from it according to what your own needs are. Now, next is interpretation and analysis. As I said, in processing itself, you are processing according to your needs, and you're interpreting and you're analyzing according to your need as well. Whatever you want to study from that particular data, you are going to analyze it accordingly. And then we have the application. Now, the application of remote sensing and GIS is not only confined to the subject of geosciences. Remote sensing and GIS has now become this new frontier, I would say, where each and every field is trying to use this particular tool for various reasons. I have this slide as well in the future slides, where I will be talking like why are we using remote sensing and what is the need of it. Now let's move to the next slide. Now, yeah, as I was talking about electromagnetic spectrum. Now, as I said, that electromagnetic spectrum is actually, it has different kinds of rays. Now, I'll not go into much detail or much technicalities of it, like, as I do not know how many of you have physics background, but you must know that electromagnetic radiations actually have they have this duality. They behave as a wave, and they behave as a particle as well. Now, I'm not going to go into that, but it just brushing up in a very precise way, I'll just say that the electromagnetic spectrum consists of specifically gamma rays, X-ray, ultraviolet rays, infrared rays, radar waves, and microwaves. Now, gamma rays, X-rays, these are actually not used to study Earth objects, but then if you are a planetary scientist, or if you are a planetary geologist, you are studying the different outside planets, you'll need these rays. These rays are actually studied to observe and analyze different, far located celestial objects. Ultraviolet light, as I said, that if you are studying the atmosphere, you'll need the ultraviolet light. For infrared rays, now visible light, infrared rays, these radar microwaves, these are actually used for studying and for various other applications it has when we are talking about Earth. Now this radar visible light, so all of you know, whatever we see, whatever we perceive through our eyes, that is the visible light, consisting of Vidyot, that is the 7 colors within it. And radar, microwaves, or let's say radio waves, if in the end you are seeing this radio waves and all, radio waves are specifically used for this communication satellites, for whatever the TV broadcast, whatever channels you are watching, it has to be broadcasted, right? So these are broadcasted using these waves because the wavelength of these waves are very, very, very high. And as you can see here, it shows frequency and it shows wavelength in this particular column. If you know this particular formula, where it is C equals to delta V, this is for the wave nature of electromagnetic spectrum, where C is the speed of the light, delta is I'm sorry, it's lambda. C equals to lambda V. So lambda is your wavelength and V is the in frequency. So frequency and wavelength are actually inverse to each other. So from gamma rays to radio waves, if you notice, the wavelength keeps on increasing, and because the frequency is inverse to it, the frequency will keep on decreasing. So remember that. Now next here I have given, it's the same table where I've shown you the specific wavelengths and the frequency. Now what I want you to notice here is that in infrared, it has various other subdivisions as well. We have near infrared, short wave infrared, and we have accordingly their frequencies and wavelengths as well. But here, what I want you to notice is that, do you see here gaps from here from okay, actually it is not visible here. Okay, now here there is a gap between 3 to 14 micrometer. There are actually atmospheric gaps. As I told you before, it's actually not visible in this data. I'm sorry for that, but actually from 3 to 14 micrometer you cannot use the entire wavelength for uh, for thermal infrared studies, because here the atmospheric, you won't find atmospheric windows all throughout from 3 micrometer to 14 micrometer. And regarding the unit, this THZ is actually terahertz, which is actually 10 to the power 12 hertz. Hertz is the unit of frequency here, and gigahertz is, if I'm not wrong, 10 to the power 8 hertz it will be. So whenever you are measuring frequency, it will be measured in hertz, and wavelength, it is either in micrometer or in nanometer or in meter or centimeters, whatever it is. This is for this slide I have kept it for, like, for visible light range I have kept their wavelengths. This is particularly in nanometer the measurements are. So you get from, like, from which range to what range, what is the wavelength of the violet color or the blue color. And this here, when you are seeing this P band, L band, S band, now these are microwave bands. I do not know how many of you have heard, but recently, in a very near future, ISRO and NASA are doing a collaborative project where they are coming up with a satellite called NISAR, and it's actually a synthetic aperture radar where they will be using 2 synthetic aperture radars. I'll be talking about it in brief in the later slides. And here, those actually, that dual SAR apparatus are going to use microwave bands. Now, how we use microwave bands, why do we use microwave bands, I'll discuss about it later, but I just wanted to show, I just want to show you that these are the particular bands which are involved within the microwave electromagnetic radiation. And for particularly in NISAR, where ISRO and NASA are working together, we have L band and S band. This is actually for the first time that this dual SAR are being used to study the objects, and 2 bands are being incorporated at the same time. I actually do not remember which organization is responsible for which SAR and which band accordingly, but I know that LS band are in used in this particular NISAR object, and one NASA is working with one band, and ISRO is working with the other. Now next is types of remote sensing, right? So as I mentioned you before, I briefly mentioned the 2 words, active and passive remote sensing. Now, in what happens is that, as I said, that in the daytime you have the sun's illumination, right? So you do not have to worry about the source of electromagnetic radiation. But what about the night? You need electromagnetic radiation there as well. So you provide your own source of energy, and depending on these two criteria, we have two types of remote sensing types. One is the passive remote sensing, and one is the active remote sensing. Obviously, by the name you can get it that passive is used for when the sun is the only source of illumination. The satellites which are using the sensors for this only, they are called passive remote sensing satellites. And the ones that are using their own source of illumination, we will talk about it in detail a little bit, a little bit later. So those are called active remote sensing satellites. So this is a very simple generic division. Now, yeah, now coming to types of remote sensing. Now, this is previously we were talking about types of remote sensing from the point of view that, okay, what source of illumination it is using. Now we will be talking about what kind of technique it is using, how many in electromagnetic radiations it is using, what is the usage. Depending on that, we have five types of remote sensing. Now let's talk about multispectral remote sensing first. What happens in multispectral remote sensing is that we use primarily two electromagnetic radiations here, that is the visible one and the infrared one in multispectral. Mostly the near infrared and the short infrared bands will be involved in this kind of remote sensing. And what we are studying in this multispectral remote sensing is that we do LULC, like land use, land cover maps we are making, where you want to know what kind of, how many, like you want to differentiate, you want to classify, you want to know that in this particular area how many roads are there any roads, what kind of vegetation is there, or let's say if there is any locality there, if the how dispersed are the localities in and around. So for that, multispectral remote sensing is used. It's quite widely used. What you see in Google Earth maps, that is multispectral data. Actually, as I said, it uses this sensor, or let's say satellite Landsat 8, and that is a multispectral data set that you have, that you open whenever you open a Google map. That's a multispectral data set. Now next we will talk about the microwave remote sensing. Now, what happens in microwave remote sensing is that, just by the name of it, you can relate that yes, it uses microwave uh, radiation, electromagnetic radiation specifically in this kind of remote sensing. And the thing is, in this microwave remote sensing, what happens is that, as you have seen in the wavelength chart, as I showed you, microwave comes quite at the bottom, right? Which means that the wavelength of microwave is much, much higher than the wavelength of other visible, or let's say infrared radiations. So with such long wavelength, higher wavelength, what we can study is that we can actually study how particular objects look in that kind of remote sensing. I do not have an image right now in my slide. I'm sorry. If possible, I'll involve it tomorrow in tomorrow's workshop. I'll show you pictures of what a microwave data looks like, how a thermal data or a hyperspectral data looks like. So in microwave data, what you will see is that it has, basically we have synthetic aperture radars, right? So these are actually antenna like radars which are situated within the sensor or in the satellite. And from there, in microwave remote sensing, it does both passive and active remote sensing, both. Like if it not only depends on the sun's illumination, they send their own signals as well, and then they calculate the time that the signal is taking to return back from the target object. And based on that calculation, it gives you the analysis, that like what object did it hit, what object is it like for example, when cyclones hit Orissa, or let's say any other coastal region in India, what happens is that flooding is commonly seen in those regions. So in those regions, we use microwave remote sensing mostly, because in microwave remote sensing, we can detect the water inundated areas more easily than in any other remote sensing data, because it shows crystal black. Now this thing also, there is a whole science behind why what happens in microwave remote sensing, I will discuss it in that 3-week workshop when we are having it in next month. If you want, you can join it, and you'll get to know more about how microwave remote sensing works, what is the what are the algorithms working behind it, what is the technique behind it, what are the various interactions, how does the microwave remote sensing, microwave data interacts with the atmosphere or interacts with the earth's objects, and how different kind of scattering, absorption happens, and what do we see in an image when we get the final result back. But in a very precise manner, I would like to mention that in microwave remote sensing, what happens is that if a surface is very smooth, let's say for example it's a very smooth pavement, or let's say it's water is supposedly, if it's like a still water, let's say like a pond or a lake, you will get a very dark pitch color in the image. Okay, and if you have a very disrupted surface, like for example like sea, you are studying sea with microwave data, so you will have waves, which means you will have disruption in the surface. If you're taking data from, if you are studying the data from those waves, you will see that in a microwave image, you will see the image will not be pitch black. It will be the pixels will be black and white, black and white. I'll show it to you tomorrow. I'll get the pictures tomorrow. I'm sorry I could not involve it today. So I'll show you the picture tomorrow. You will get to know how actually a microwave image looks like. So that's how we study it. Now in lidar, what happens is that in lidar we are using infrared lasers to figure out different objects. In lidar, what we are doing is that lidar is not used in satellites. What we do is that we take an airborne, or let's say an instrument or a vehicle is there, and on it a sensor is attached, and in the sensor we have the lidar sensors, right? And from those sensors you have this infrared lasers coming and hitting your target. So from that you can actually gather information, whatever like when they hit the target, they come back to you, right, to the sensor. So whatever time the lasers are taking back to come back to you, you can calculate that. And it is actually used mainly for in 3D surfaces. To build 3D surfaces, lidar is actually very useful. If you want to have 3D mapping, if you want to do a 3D mapping of a house or of a tree or of any other object, you actually do lidar mapping. Next, we will go to hyperspectral remote sensing. Now, hyperspectral remote sensing is very different from the other remote sensing types, because here we are talking about different, the mechanism behind hyperspectral remote sensing is quite different. See, it has all the bands as a multispectral would have. It will have your visible, it will have your near infrared bands within it. It will also have thermal bands within it. But the difference in hyperspectral and multispectral is that in multispectral, the number of bands are very less. In hyperspectral, the number of bands are very more. Which means what? Basically, it means that it is studying very minutely whatever data it is going to study, whatever uh, uh, you know, uh, energy it is going to study in a very minute way, in a very detailed way. In multispectral we don't get such detailed information about the object, but in hyperspectral we get very specific details. So if you are a geologist and you want to go for mineral mapping, hyperspectral is the only remote sensing technique that you should go for. It's not like we don't use multispectral, we do use multispectral, but it does not give you a very accurate information. If you're using hyperspectral data for mineral mapping, what happens is that you get accurate curves, accurate spectra. You know this, right? Like every object has a unique spectra attached to it. When this particular electromagnetic radiation hits the surface of any target, it will generate a unique spectra. It will have its own signature, just like our own thumbprint. You have your thumbprint that is very unique to you, right? It's not the same as any other person's. So similarly, each and every mineral, each and every object has a unique spectra attached to it. So hyperspectral actually studies those spectra, and that's why for minute studies it's used. Next, we have thermal remote sensing. Thermal remote sensing is actually one of the most upcoming remote sensing techniques, where much research has not been done as compared to multispectral, hyperspectral, or let's say microwave remote sensing. Thermal remote sensing. So in thermal remote sensing, what we do is that the basic fundamentals behind it is any object that is that whose temperature is above 0 Kelvin will emit energy. right? So thermal remote sensing is actually measuring that energy. It is not measuring the amount of energy that is being reflected. It is not measuring the amount of energy that is being scattered. It is actually measuring the amount of energy that is emitted. There is a difference between these kinds of energy interactions. It is going to study the amount of energy that is emitted from a particular object depending on its surface temperature, depending on its kinetic temperature. And as I said, there is a whole working behind it that we'll be discussing in that 3-week workshop that we'll be discussing on our later, probably in our next month. Okay, now here we will be talking about sensors and resolutions. I'll skip with this resolution part in a very brief way because I think I've taken a lot of time. This workshop was supposed to be of 1 hour, and I think I'm running up very late. I'll just it is written in a very nice descriptive way. So when you will get the PPT, hopefully you'll all be getting the PPT. You can go through it and you will understand what I'm trying to talk here. But I'll just give you a brief idea about the resolution of the sensors. So sensors are what? They are basically electronic devices which are used to study the detect the presence of the object, or they are used to study whatever data is coming from the object, or whatever interactions or whatever information you want to gather from the object. So that is studied by the sensors. Now sensors have different types of resolutions. Now we will be discussing about this resolutions. Oh, I'm so sorry. Yeah, so we will be discussing about these resolutions. So first we have spatial resolution. Now what do you mean by spatial resolution? Now when I'm talking about a particular sensor having a spatial resolution of 5 meters, what does it mean? It means that if this particular sensor, for example, this sensor is situated within the satellite, and this satellite is taking data right now. So if I say that the spatial resolution is 5 meters, it means that if any object within its field of view is separated by a distance less than 5 meters, it will not be able to differentiate these two objects. If any object is separated, for example, by a distance of 10 meters, it will differentiate between these two objects, and in your data you will be able to see, yeah, okay, I have these two trees here in the image, they are separated by a distance of 10 meters, let's say. If in reality, if there are two trees which are separated by a distance of 3 meters, when the sensor will take the information from this from this particular object, what you will see in your data is that you will see only one tree instead of two trees. You will see only one tree there, because it could not differentiate the two trees there because of its spatial resolution, because of its coarse spatial resolution. We use the word coarse, means it has a coarser spatial resolution, means that it cannot differentiate between objects having a particular distance. Like for example, if I'm talking about, if I say that it has a coarser spatial resolution, it means that let's say it has a spatial resolution of 100 meters, or let's say it has a spatial resolution of 50 meters. So it's actually a loss to us if you really think about it. If you really want to differentiate between very minute objects in and around you, you should not be using coarser spatial resolution sensors. You should be using finer spatial resolution sensors, for example 5 meter, for example 1 meter, uh, for example less than 1 meter, or maybe there are sensors which are measuring 30 centimeters within, have a spatial resolution of 30 centimeters. So that works. So next we have spectral resolution. Now spectral resolution here, see, as I told you just now, the difference between hyperspectral remote sensing and multispectral remote sensing, right? So here the spectral resolution plays the most important part in that difference. It is actually the ability of the sensor to define very fine wavelength intervals. The finer the wavelength interval is, the more precise you can know, like the interaction between a certain object and the electromagnetic radiation. So that spectral resolution is the is the make or break resolution when I talk about hyperspectral and multispectral remote sensing data. Now radiometric resolution. Now radiometric resolution means how much information is stored in a pixel. You have an image, all of us know, we have cell phones, we know that we know what pixel means, right? But we do we ever give a thought about how much information that pixel is storing that we have in our phone, or let's say we have in our sensor, or we have in our satellite? Why do you think that a DSLR takes a better picture than a normal Android phone of, let's say, 15-20,000 that we own right now? It is because the radiometric resolution of DSLRs are much more than the one cameras inbuilt in our mobiles, handset mobiles. So what happens in radiometric resolution, as I have given an example, that it stores the information and we measure the information in the in bit. So if I say that this particular sensor has a radiometric resolution of 12 bits, it means that it has 2 to the power 12, that is 4096 shades of blue in it. That means it can differentiate the shades of blue. Like for example, let's say the electromagnetic radiation is hitting a target, right? The interaction of each and every particle within that target is going to react differently to that electromagnetic radiation. If the radiometric resolution of the sensor is very, very high, it will be able to capture that much of information. If the radiometric resolution is very, very low, it will not have these many shades of blue. It will just have very like 2 3 shades of blue it will have, and it will not be able to differentiate that minute differences between two objects, or the between a lighter shade or a stronger shade, or even let's say we are studying a water body. Now everywhere the water is not going to be the same, right? But if we have a higher radiometric resolution, we will be able to understand, okay, the water here is if it is reflecting a lot of green color, maybe it has a lot of algae content in it, or things like that. So by radiometric resolution, it means how much information we are getting. Temporal resolution, now this is a very, very important resolution that a sensor needs to have if we are studying a particular place, or a particular object, or basically it is used for particular locations where we are trying to notice changes over a period of time. The temporal resolution means like by how many intervals the satellite is going to visit the same location. We know that the satellite is revolving around us, right? Which means that if today it is above me, after a certain amount of days, after when it has completed its entire one rotation, it will again come above me, right? But if I am in a field, like for example, as I said, I'm studying disaster management, and I want to know on a daily basis how much of damage a particular cyclone, or a particular or let's say there is tsunami, there has been tsunami. So how much damage has it done to to a particular location? I need to know the data, I need to know this information day after day. I cannot wait for another 7 days to see what has happened in that particular area. So for that, I need sensors which has higher temporal resolution, which means they will be revisiting that particular location within a very short frame of time. Now, next here, I have given you a list of, some of the, it's not the entire list. There are many, many, many sensors. There are many, many, many satellites. There are going to come many, but just to give you a rough idea, you on the extreme left hand side, you have the sensors. Then you have the number of bands within them. You have the spectral regions, which means what are the what are the measuring, which electromagnetic radiations are the measuring. You have the spatial resolution, their swath. The swath, I told you that it is the instantaneous field of view, like at a time when a sensor is looking down on earth at a particular second, how much of area is it covering, that is swath. Then next we have quantization or bits. It means the radiometric resolution, and temporal resolution, you have it in days here, right? Now I'll just skim through it, and I'll give you some small examples from it. Like for example, Hyperion. Hyperion is actually a hyperspectral remote sensor. So if you see, the number of bands is 220 here, which is much higher than any of the number of bands that you are seeing in the other satellites, because it is a hyperspectral remote sensor and it needs this many bands to work with. But if you see that the amount, that the spectral regions that it is using, it is very much similar to any other sensor. Also, you will see its spatial resolution is not that much. It's 30. If you use average ng, you will get 8-meter spatial resolution. But then average ng data is actually not, I don't think so, it's a spaceborne data. I think it's an airborne data. And then again, if you see, yeah, if you see here, now this MODIS, the Sentinel-3, they are covering a very large area. And then again, that's why they have a very coarser resolution, because the swath is very large. You are seeing 2330 kilometers it is covering at the same time, which means it has a very coarse resolution. You cannot differentiate objects within, if they are placed within 2330 kilometers of distance, which actually does not work in most of the cases. But then again, if you are studying, you will need this data when you will be studying very large areas. You want to study a very huge area which is much more larger than this 2330 kilometers. So at that time you can use MODIS. however you want. But if you want to go and study very minute features, so then here if you will see, you have in the extreme end, you have this worldview 3 sensor, which is having a swath of 13.1, which means it is covering very less amount of area at a time, which means it has got a very high resolution. Okay. And in number of days, you will see that, okay, now Modi's, although it has a very huge swath, but then at the same time, it will have temporal resolution of 1 days. Now, it is very understandable. If you really think about it, if I am covering a large distance at a time, obviously my temporal resolution will be less, because I am covering a huge area. So for me to cover the entire Earth, the entire rotation, it will take me less amount of time. If I'm covering a very small area, if I'm going ahead and I'm covering very small area, it will take me more number of days. So obviously, I'm not saying that they are all the time like inversely proportional to each other, the radiometric and temporal resolution, but you can give, you can relate the two. Now, next we have aerial photography and the idea of photogrammetry. Now, we have been all this time I have been talking about satellite photographs, like how does the satellite work? How does the satellite capture images? How does the satellite capture the energy, and how do we analyze it? Now, let's talk about aerial photographs and why do we need them? Now, the photogrammetry is actually the science of measuring objects or products from aerial photographs. So now, in aerial photographs, what happens? There is an aircraft. The sensor is placed on the aircraft, and from that aircraft you are getting the pictures. And what you do is that there is a instrument called a spectroscope, and you use that instrument to, I'm sorry, it's not a spectroscope, it's stereoscope. And you use the stereoscope to view the aerial photographs, and from that you can actually calculate the you can actually correlate between the scale of the objects in that image, because you already know what is the scale to the ground reality. So these are few pointers that I have mentioned, that you can, that is why aerial photographs are used. Basically they are used for measurements. Now there is a entire calculation behind it, how you can measure these things. We will discuss it again in details in our that 3-week workshop. If you are interested in knowing how aerial photograph is studied, and how do we calculate from an aerial photograph, I can give you I'll be giving a very mathematical idea about how to make those calculations. So you can join that course if you want to. So but just to tell you about it, we determine the scale of a photograph, we determine the various area measurements, how much area is it covering, you determine how much displacement has occurred. Like for example, when you are taking an aerial photograph, there will be some sort of distortion, there will be some sort of displacement. Accordingly, it will not be exactly the same as the ground itself. So we make those calculations as well. And we can also determine object heights and terrain elevations. Now this is the main criteria for doing aerial photogrammetry, or you're using aerial photograph. You want to measure the height of the objects, you want to get an idea of the terrain elevations, especially if you cannot go to that particular area. To us geologists, we study aerial photographs in very detail, because we want to know this because we want to get an idea of like the object heights, or how the terrain is there. Right. Then, okay, now this is an image, this is an aerial photograph here that you have. Now, this is as you can see, now these patches that you are seeing is actually the agricultural lands or farmlands, as you say, cultivational lands. And you can clearly see the patches here, and you can clearly differentiate. These are the roads. This is probably some industry. These are houses, but it looks more, yeah, these are houses or industries or warehouses, something like that. Here on the upper right hand corner, you have an entire suburb locality here. So that's how an aerial photograph looks like. I wanted to show you this. Now next we have visual image interpretation. Now what happens is that you have a satellite image in front of you. The first thing that you do is that you visualize the image. You look at the image. You start to analyze the image. first you get an idea of it, and then you start doing your process. You need to know, right, like what what is there in that particular image, what does it have. So there are many elements while we do a visual image. So this is a chart basically I have given here. So we what do we study when we are looking at a particular satellite image? What do we study? We see the tone and color of the various objects that we are seeing. What color is it? Is it green? Like if you open the Google Earth, you will see the tone and color, and you will know if it is a road, if it is a building, if it is a vegetation cover, if it is a forest. You will know it directly. Next, you see the size, shape, texture. Of course, if you're looking at a vegetation, it will have a very coarse texture. If you're looking at a water body, it will have a very smooth texture to it. The size and the shape. Now see, if it's a very small circular water body, you will know it is either a pond. If it's a little bit larger in size, you will know, okay, it's a lake. The shape of it also tells you a lot about the water body. Like for example, if you're looking at a swimming pool and if you're looking at a pond, both might have the same size, but the shape of both the things will be different. Right, in a swimming pool you will have a very rectangular, a very crisp boundary you will find if you are viewing a swimming pool. But if you are viewing a pond, if you're viewing a lake, it will not have a rectangular boundary or a square boundary. It will be very irregular in shape, right? So you will know by you if you study these things, you will know, okay, what am I seeing here. Now you see pattern, you see height, you see shadow as well. Okay, like for example, you want to study uh, uh, let's say you have a flyover, right? So if there is a flyover in an aerial image, how do you know? In an aerial image or in a satellite image, the image is from above. You are not seeing it from sideways. You're seeing the image from above. So you won't know whether this is a flyover or this is a road. So the only thing that you can differentiate between a flyover and a road is because of the shadow. A road will not have a shadow. A flyover will have a shadow beneath it. Next, the height. Again, tall buildings will have shadow. You can, just by looking at the shadow of a particular building or a particular pole, you can know, okay, how much tall it is as compared to the other buildings near about it. You cannot really look from above and say from an eagle's point of view, okay, this building is taller than the other one. You cannot say that. But looking at the shadow of it, you can actually figure out, okay, what is it. Then there is a pattern. Like in the previous image, I told you that, okay, if you see in the right hand corner, I said there is a suburb, but here in the southernmost part, I said it's an industry. Why did I say that? Because there is a pattern to it. These between these lands, I told you, these are cultivational lands, because there is a pattern to it. You can see patches. If it was a forest, there wouldn't have been patches. Now this is a very proper demarcated boundaries you see in this agricultural lands, which means these are agricultural lands. So you look for these patterns when you see an image, right? Then you have site and association. Okay, where are you seeing what? That matters a lot. Like in the next image, you will see, okay, now this is an image of Vishakhapattanam. I could see there were a lot of probably international students are also joining us, if I'm not wrong today. So Vishakhapattanam is actually a port city in India. So here I will specifically talk about association. Why association is important. Here, if you can see in your screen, I do not know how many, if it is visible to you. If you look at my cursor, okay, here there are two dots. What do you think these dots are? Now, this is a sea, and I told you that Vishakhapattanam is a port city. So, what can probably be there in the sea? In a very small scale, like in a very, like the size of it is very small. It's looking very small. So obviously, this will be boats. I took this image from Google Earth last night only. So probably there were some boats there. So basically, you are seeing that. Now here you can see where my cursor is. There is a smoke. So maybe this is an industry. So this is how an satellite image actually looks like. You can see here we have this urban areas, we have this entire city. So you can see how planned it is. Here we have a canal go from the sea itself. Now this particular area where my cursor is right now, this is probably the fishing port in Vishakhapattanam. You will see the shape, you will see that it is a little bit outwards towards the sea. in the very upper portion, if you can observe, you will see this ridges like structure. So there is a mountainous region there as well. Vishakhapatnam is a place where you find sea, where you have mountain, where you have a city, you have everything here. So here you can see this particular mountain ridges as well if you observe it clearly. So you don't need to start right away processing. You take a satellite image, you observe these things, you do a visual interpretation. Okay, I have this image, what can I just look at it and what can I tell from this image? So that should be how you should start your processing. You start processing with your eyes first. You see a particular image, you analyze it, you think that okay, fine, okay, this is how it is working, this is what it is. Okay, now I have this features. If I'm trying to find a particular mineral, let's say for mineralogists, if I'm trying to find a particular mineral, I won't be finding it in a suburban area, right? I'll be going and I'll be saying, okay, fine, I have ridges, I see ridges here. Like for example, in certain places, if you are looking for oil and gas, we know that, we geologists know that sometimes in the crests of the fold we find oil, trapped within the different within the anticline of the fold, or let's say the syncline of the fold. So by looking at these ridges, I know that there is a folded structure. Okay, I can see there, I can study there. So you are actually, what you are doing is that you are minimizing your area of study. So you start with visual image interpretation and then you move on to your further processing. Now, next we'll go to digital image processing. Now, this is a very extensible topic. I can speak and speak and speak on this topic, and this topic will never be over. For different remote sensing types, as I said before, we have multispectral, hyperspectral, microwave. There are different types of digital image processing algorithms. There are different techniques. There are different ways to go around it, and it's a whole story. So just to keep it short today, I'll just be talking briefly about what we do actually in digital image processing. This is a basic definition that you have, that digital image processing involves the manipulation and interpretation of digital images with the aid of a computer, right? So what are the basic steps that we do? You do image rectification and restoration. This is where the atmospheric correction comes, as I said to you in the very first early slides, that atmosphere does disrupt the electromagnetic radiation. So when you get the data, you need to do atmospheric correction so that you can properly analyze your images. So you do atmospheric corrections. In the first step in your digital image processing is that you get the raw data from the sensor, you do atmospheric correction, and then you move on to do further more analysis. Then you do image enhancements. Okay, now for example, we all use Instagram, I suppose, or we are on Facebook. You have an image, right? And it's not really very good, it's a very dull image, and you are not looking very proper. So what you do is that you use filter, right? By using different filters, you kind of try to make it, you increase the saturation, or maybe you are increasing the sharpness of your image. You make those calculations and you make yourself the picture better one. Those that the picture does not remain as dull as it was before. The same thing happens in remote sensing as well. You have an image, you want to enhance it, and you want, so you what you do is that there are various filters in remote sensing. Of course, the filters are not named as the ones that you see in Instagram or Facebook. We have different filters for that, and we have different usage of those filters for you want sharp contrast images. You want to know the sharp striking difference between a water body and its surrounding surface. You use a specific filter. You have other you have other usage. You want to tone down the differences, you can use a low pass filter. We have this terminologies like a high pass filter, we have a low pass filter. I'll be discussing them in details, as I said, in the workshop. But for today's workshop, I will just keep it to a very minimum. And then we do image classification. Now this is a very important part in remote sensing. Why are we doing all these things at the end of the day? Why are we doing all this, processing, all this gathering of data and all of it? Because we want to classify things. We want to know, okay, now we have a full vegetative cover area in front of us. Which ones are the healthy vegetative covers, which ones are unhealthy? We have a certain location in front of us. We want to know, okay, Where can we find this copper mineral, where can we find the iron minerals. We want to classify a particular image and for our own convenience. So we do that using digital image processing. This is the last step actually in digital image processing, where we do image classifications using various algorithms. There are various we have various algorithms and various what to say, uh, not like filters, but we have various other properties attached to it, depending on what kind of processing, what kind of classification you want to do. You want to do machine learning, you go with that. You want to do something else, you work according to what you want basically. Then we have data merging and integration. Now this is actually something which comes under GIS as well, so probably I'll be dealing with it tomorrow in tomorrow's workshop, where I'll be talking about how we merge different kinds of data and we integrate it to get ultimate you know we want to get an ultimate result from it. I have taken a lot of time actually, so I'll just go towards the main slides. And this is a slide where I'm talking about why should we use remote sensing. Obviously, based on my lecture of this 1 hour lecture, you have understood that we are doing it to cover large spatial areas, inaccessible areas. We want to identify objects on the ground. We want to observe the surface areas where we cannot go. Okay, and then we want to monitor the changes. Now, every time I want to monitor change in certain place, I cannot go there every now and then, right? So we use remote sensing for that. We use for it helps us in integrating different amount of data around us. Like for example, if you are manually going to some places, you have this data, you have that data, you are seeing this also, you are looking at, like as a geologist, you are looking at the mythology also, looking at the structure also. Everything becomes clumsy. In one place you are having remote sensing data, you have structural maps, you have mythological maps, you have mineralogical maps, you integrate them, all of them, and at the end you find an ultimate map which tells you, okay, these are the regions, these are the places that I will find a particular mineral, because yeah, it has a lineament attached to it. It has for example, it has certain specific structurally it can support a mineral there. So it helps in decision making as well. As I said, it is very much used for inaccessible areas. And it is used for features which use different electromagnetic spectrums. Like for example, we are only seeing through our eyes, so what we see is the only visible spectrum, right? We cannot see infrared through our eyes, or we cannot see other wavelength through our eyes, but we can study the features using remote sensing and using those electromagnetic radiations. Next, we have applications of remote sensing in major fields. Now, here I have just jotted down the different fields where we can use remote sensing. One, we have meteorology, then we have oceanography, geosciences, agriculture, forestry, disaster management. Now, meteorology, you all know that we are calculating what we want to know the weather forecast of a certain place. So we have those satellites which have very high temporal resolution, so we can get the weather forecast for that. For oceanography also, like we want to know, okay, if a cyclone is coming or not, we use remote sensing for that. For geosciences, so it has many applications. You will see in the next slide. In agriculture and in forestry, we want to know what kind of okay, in agriculture there is something called they do forest insurance. There is like insurance companies, they actually see, okay, how much if your agriculture is actually working or not, if you're utilizing your land properly or not. So for that, agriculture remote sensing is used in agriculture, and there are many other usages as well. In forestry also, you want to know it's not only in forestry, it's not only based on like classifying different kinds of flora and fauna around us, flora basically around us in forestry, but also how much of carbon exchange of carbon dioxide is happening. We can actually find there is the forestry people do calculations based on that also using remote sensing. Then in disaster management, so we all know, whether it be earthquakes, whether it be landslide, whether it be cyclones, whether it be tsunami, just name it, remote sensing is used in every other field of disaster management. Then we have surveillance, of course, by military, the military personnel use it all the time for surveillance. Planetary expedition and study of solar system, you want to study celestial objects and all, you will obviously need remote sensing, because otherwise without remote sensing, I don't think so we are well equipped right now to go to a particular planet and take samples by ourselves. Hopefully we will be there one day, but now we are completely relying on remote sensing for mapping the Milky Way, for finding out, for extending our reach in the universe, we need remote sensing. As I said, insurance claims, it comes under the agricultural field. Water resources and study of glaciers, of course. You cannot go to the glaciers all the time, right? It's a very inaccessible area, so you use actually remote sensing techniques to find out like how much melting is taking place. You can also talk about climate change based on the glacier, the movement of the glaciers and all. Then we have monitoring environmental change. Of course, if you're studying the atmosphere, if you're studying the rainfall data and all, it comes under meteorology as well. Somehow that we are studying, we can study the environmental change. Of course, we can study the biodiversity also. It comes, biodiversity comes a little bit inside GIS also, where we are using the technology of GIS, where we know that okay, fine, we have these many plants in this particular area. Okay, this is the, let's say, these are the total number of species that we are seeing, how they're evolving, how they're interacting with each other, how they're interacting with the environment. We can study all these things using remote sensing. Again, urban affairs, it's actually the most important, one of the most important uses of remote sensing. I've put it at in the end, but it is actually by most of the companies, what are they doing is that, yeah, we want to know, like, and urban affairs is closely used with GIS as well. Tomorrow probably we'll be discussing about it as well, that in urban affairs we are mostly talking about like what, what is the nearest hospital to you, what is the shortest route to this, or if I want to have a planned city, where should I do it. So these are the applications of remote sensing in different fields. Now we come to geosciences. In geosciences, I'll not take much of your time. I know it was supposed to be a 1 hour discussion, and I have like extended it to like 13 minutes now. I'll take another like 5 or 10 minutes. So all the students here, I can see there are 98 participants. You have been with me, so please bear with me for another 5-10 minutes. I hope that I'm not boring you guys. So now the great combination of remote sensing and geosciences. Now we will talk about geosciences. So I'm a person from geosciences. I want to particularly focus on this particular topic. Okay, in geosciences, remote sensing plays a very vital and important role. First of all, it helps in accessing remote areas. This is a constant struggle for geologists. All the time we cannot go to most of our fields, as if geologists are hearing me, you can relate. Most of the time our fields are in inaccessible areas. We do not find we don't do field work in urban areas, right? We do it in the top of a mountain. We have to trek and go for like kilometers and kilometers where we find our particular site, and it is very it's very tiring. So what we do is that we can use remote sensing for those areas. I'm not saying that depend on remote sensing completely. Of course, you need to know and go and check the ground truth as well. But for example, you are trying to do drilling in a particular area. You want to find if it has oil or not. If you want to find if the particular area has minerals or not. You can obviously go for a reconnaissance survey using remote sensing. If you are using remote sensing in the beginning of your work, it will definitely reduce your area. It will reduce your area, and then you can have, instead of having hundreds of kilometers in your hand, you will have a few kilometers, and then you can go for manually you can go there, go with geophysical investigations. You can do the well drilling and all. But in the very first stage, you need to do remote sensing, because it will not only save your time, it will also save the amount of energy and the the uncomfortability of going to these places and staying there and doing your research or doing your work. Next, it helps in integrating various data. Now see, you're using a computer, you have everything in a particular data set. You want to overlay two maps, you want to, it becomes easier. Definitely it will be easier. You have handmade maps in your hand, and you have maps in your computer. You know what the difference I'm talking what is the difference that I'm talking about. You have all the information stored in a single place when you are using remote sensing, and it comes in GIS as well. I'll be talking about it in GIS as well, where we are storing all the different data. And geology is a field where data is enormous in geology. Like, speak of whatever you want, like whatever field you take from geology, we have enormous amount of data. For example, if I'm talking about making a structural map of a region, you have so many data that you go to field, you gather so many data. You have this number of lineaments, you have the dip, and you have a strike. So if you can just gather it in one place, it will be so much easier to integrate it with your other data that you have. Like, for example, you have a geomorphological map, you are overlaying the geomorphological map with the structural map. It will give you such a clear clear idea ki, okay, this is a heightened, this is a mountain that I can see in a geomorphological map. Beneath it actually is a fold, and we are finding this anticline. Probably it has a plunge. It has a plunge in this particular direction. You can study more. If you can integrate data, you will gather information in a very quick time and in a very accurate way. It helps in reducing the time of operation. Obviously it will do that, and it helps in mapping larger areas. Of course, you want to cover a larger area in a smaller amount of time, you will need to utilize these tools. Now next we have all the branches where remote sensing is extensively used. Okay, now we do geological mapping. Let's say whatever mapping it is, you want to do structural mapping, you want to do lithological mapping, you want to do mineral mapping. Mapping is important in geology. Without maps we are nothing. All the geologists know that. So you have to use remote sensing in that. Next we have lithological classification. Yeah, for a particular you want to see what the lithology
Like, ma'am will be joining now due to some network issues, I think so. Please be on the class. No, no, it's not over.
Yeah, I am so sorry. Actually, my what was that? Yeah, this one. Yeah, my I connected it. Can you all hear me? I'll start the
Yes, ma'am, we can hear
video.
you.
Okay, okay, okay. Actually, my Wi-Fi was connected to the laptop, and my electricity went off, so even the Wi-Fi got disconnected. I'm very sorry for the delay. So I'll just finish it up in a very quick way. We have a few pictures here only. So as I was talking about, so the different branches of geology, I'll put it on slide. Okay, yeah. So different branches of geology. So you need for like lithological classification, as I was talking about, you need to know the lithology. You need to know you can use it for studying geological structures. You will use it for seismology. You can use it for planetary missions as well, for geomorphology, geohazards, in engineering geology. In engineering geology, what happens is that you want to build a tunnel or you want to build a dam. So what happens is that you want to know if a particular location is suitable for making a dam. And we all who have studied engineering geology, we all know that there are various factors that you take into account before you actually start deciding that yes, okay, this is the location where we want to build a dam. You have to see where you are getting your raw materials, if how much costing it is going to take, if it is going to be stable in that particular location. For example, in high mountainous terrains, when there are dams, they really have to take into consideration, okay, if there is a chance of landslide, if there are chances of earthquakes happening, how much stable will the structure be. So for coming to those conclusions, for those decision making skills to happen, you take help of remote sensing. So then we have environmental geology. Then you study the terrain and dam analysis. Dam is digital elevation model, which gives you the idea of an elevation of a particular area. So then we have mineral exploration, geothermal exploration. Obviously, you for mineral exploration, you study actually the hyperspectral remote sensing data primarily, where each and every mineral has their own specific spectra, and these specific spectra are actually they help you delineate like, okay, this particular area that I'm studying, okay, this has copper, this has iron, this has muscovite, this is mica minerals. So for that you can use remote sensing. For geothermal exploration, I told you about oil and gas. Even when there are cases where you have heard about oil spills, right? Well, oil was being transported, or there are pipelines beneath the oceans, and somehow the pipelines got bursted and the oil spill occurred. For that, to detect the oil spill and how much of damage it has done to the surface, to the ocean surface, because oil spills are very much harmful for these fishes and other living organisms in the sea. So to study that, we actually use microwave remote sensing, because as I told you, in microwave remote sensing, very smooth surfaces, they show pitch black in microwave data. So if there is an oil spill in let's say in an ocean or in a sea, you can actually see it it is very visibly clear in a microwave data. Then you do modeling, multi-temporal analysis, and classification as well. Now modeling I will explain in the later on images actually, and multi-temporal analysis, as I said, for disaster management scopes, or if you are studying seismology of an area, you will need to do multi-temporal analysis now and then again. Now we will go to this is the last part of the slide where I will be just showing you some of the images where we are actually studying studying the remote sensing data. Now this is from a structural point of view. This is for all the people who are living outside India. This is a city called Dehradun. This is near to Himalayas, and here the main boundary thrust, the Himalayan frontal thrust. These are most famous, thrust boundaries when we talk about the Himalayan tectonics or Himalayan orogeny. So here you can see, if you just look at the satellite image, you can see this yellow boundary that has been drawn here. So this is actually, you can delineate it just by looking at the image itself. You can actually see that in the image itself you can differentiate between the Himalayan frontal thrust. This is the main boundary thrust, right? Now this is the city Dehradun. It's a little bit coarser resolution, so you cannot see the city, but here it is the city. Then you have here this Piedmont zone, and here they have delineated this Piedmont fault. We will talk about this Piedmont fault and all more in details when I'll be talking about in the workshop where we'll be dealing with remote sensing while using geology, the usage of remote sensing in geology. We will discuss about more like how to recognize them, so that's how you actually differentiate, you actually find out, or you map the particular area based on what you want. Now this is a seismic zonation map. So that's how, you know, you have you see a map and you know, okay, fine, I live in northeastern part of Assam, okay, this comes under red zone, which means this is zone 5, which means this is a highly seismic area. So that's how a map actually looks like when you are integrating different data from different remote sensing sources or from GIS, and at the end you come up with maps like this. So it helps a lot. If, for example, if I want to build a tunnel, if I want to build a dam in northeastern area, my techniques will be very different from the areas here which are white zone, you know, like for example in Hyderabad, this comes under white zone, that means it's zone 1, that means seismicity here is very low. That means that when I am trying to build a, for example, I want to build a dam in Hyderabad, my techniques, my you know, my thinking while building a dam or whatever I'll be using, it will be different than the dam I built here in northeast. Here I'll be using more of, I'll be looking, I know that it is an earthquake prone area, so I'll have to take extra measures so that you know, the dam is not hurt in any way if in any case you know, earthquake occurs. Next, this is in terms of planetary sciences. This is a map of Mars, and I think you all know Olympus moons and Encelum moons and all. These are the famous volcanoes, and that's how actually how a planetary map looks like when we all we the ultimate aim of using remote sensing in planetary surfaces is that we want to map the different planetary surfaces, because if you have this future of traveling to these planetary surfaces and colonizing planetary other planetary surfaces, we need to know, okay, what is where. So in when I talk about planetary geology, what we do is that we look at a particular planet or a celestial body. We measure, we see their composition, we see their mineralogical structure, we see the other structures there. We see okay, how to correlate them with the origin of the Earth. Those are there, of course, and then again the colonization of celestial objects also come into play here. So we want to know, okay, these are the areas. Again, if you want to land, if I'm looking at this particular image, and for my next space mission, I want to land, where should I land my rover? It has to be a plain area, it cannot be a mountainous terrain, otherwise a rover will not work there. It has to be a planus, it has to land somewhere. So for all these decision making criteria, we use remote sensing. Now here we are, this is where I wanted to show how geomorphology is studied using remote sensing. You can see this is a meandering river. Now this is actually, I think it's taken from an aircraft where you are getting a very angular view, and this is from a satellite where it's downloaded from USGS, as you can see. USGS is a website from where you can actually download free material, satellite data. So if anyone wants to download like Sentinel data, Landsat data, you will find it in USGS site. You can create an account and you can get it there for free. So you can see how a meandering river looks like, and how does this, you see the river has actually changed its course. Like previously it was meandering in this way. If you can look at my cursor, the previously the river was meandering in this way on the, I'm talking about the right image, uh, and then it just changed its direction, and it straightened its path. So that's how we actually study. We can study oxbow lakes, and here also on the left hand side image, you see these are all oxbow lakes and all. You can actually see on the left hand side image, there are, you can see these patterns. Basically the river was flowing in this way, and then it changed its course on over the ages. Now this is mineral mapping. Now this is an image I have taken from a research paper. There we have, there they have shown how they have done mineral mapping for the entire continent of Australia. So you can see, they have given an entire list of what base metals they have found and what minerals they have found. So that's how, at the end of the day, you want to get the spectra of minerals, and what do you want to do, what do you want to do with that spectrum? We actually want to make map of that, of those minerals, and then we want to go to the ground and we would like to say, okay, are those minerals in proper amount, and are they in proper quantity, so that they can be mined. So that's it, that is our ultimate objective here. So that's for that we need to make mineral maps. And I think, yeah, this is our last slide before I end today's workshop. here I'm talking about modeling. As I said, I will be talking about modeling later on. Here I've in the on the left hand side, you can see there is a model where I'm implementing GIS. I'll be talking about this model more tomorrow, actually, because it implements GIS data along with remote sensing data. So it is about integrating data, as I said, as I told you in that slide where I was talking about, digital image processing, and I told you that yeah, we actually in the end we integrate data, and we want to analyze it, and we want to use it for our own advantage, or whatever usage we want to use it. So this is an example how a particular model works. This Newmark model is actually used for finding out how it's actually used in landslides, like how susceptible the landslide, a particular block of land is susceptible to landslide, basically, like how a particular block of land is susceptible to landslide. We find it through using a Newmark model. And on the right hand side, you can see there is a landslide zonation that has occurred. If you really, when you will get the PPT, if you will zoom it, you will see that it has the green one is the lowest low, and the red one is very high, which means the red portions have this very high susceptibility to landslide, and the green ones are safer regions. Talking about the left hand side image where we are talking about model, you can see here we are considering so many information before getting into a conclusion whether a particular area is prone to landslide or not, and how much it is prone to landslide or not. So we take into account the soil, the geology, the INSAR data. INSAR data is basically microwave data. We take digital photogrammetry, we make a demo of it. We consider the slope, cohesion, friction angle. We see the static factor of safety. We see the critical acceleration, right? We also take seismic source characterization. That means if there is an earthquake, what is the source? What is the magnitude? We take the ground motion of the earthquake, and we see, okay, how much impact that earthquake is going to have on this particular block of land. If there is an earthquake at say this, let's say for example at 10 kilometers away from this particular land, this particular slope, there is an earthquake. Is there a chance of high landslide? Is there a chance of low landslide? We come to these conclusions using these models. So that's how it is used. I'll talk about it in detail tomorrow as well, when I will be talking about GIS and the usage of GIS in remote sensing. I'm sorry, uses of GIS in geosciences. I think I've spoken for quite a lot of time. Today I've taken a lot of your time. Tomorrow I'll try to wrap it up within 1 hour. So that's all it was for today. In the end, I just want to say that, okay, whatever we have discussed, I just gave you a very brief idea of what remote sensing is and how it is used in geology. We actually are planning on a workshop, on a three week workshop next month. Preferably it will be next month. Right now, early registrations are going in. So these are the details that I have given here, and this is the registration link. This is the WhatsApp group. You can join the WhatsApp group. You can register using a Google form for if you're interested in the workshop. It will be very detailed workshop where I'll be talking about remote sensing and the various algorithms working behind it, and how in details how we do analyze remote sensing data in geosciences. Today I gave you a very brief, I gave you I gave you guys examples of, okay, this is how, this is this. In the workshop I'll try to give you more insight into it, like how we achieve those maps, what are the steps that we do, like right from the beginning till the end, from collecting the data till getting the ultimate result of geological maps in our hands, how we do it. I'll be talking about those things in the workshop. So if you have liked today's workshop class, do attend tomorrow as well. We'll be discussing about GIS and implementation of GIS in geosciences. And if you did like whatever we discussed today, and if you would like to know more about it in details, you can register to this particular workshop, and you can contact the people who are organizing it. You can contact the Advantage. They have their own LinkedIn page. They have, I think they are present in Facebook as well. You can also ask them in chats. So that was it for today. Thank you for your time and for your consideration, for listening to me for such a long time. Thank you very, very, very much. Are there any questions that you would like
Yes,
to
ma'am.
ask
Regarding the
me?
questions, like there were many questions in the chat
Yeah.
box. Since you have been
Okay,
left
okay,
out,
okay.
so those messages
Oh,
have
okay,
been
okay, okay.
automatically deleted.
Oh,
So what
I
we'll
am
do is
so
tomorrow
sorry
we'll
for
just
that.
make an half an hour extra session for the doubt session. We'll keep a
Sure,
doubt
sure,
session
sure,
so that we
sure,
can
sure,
clear
sure,
all the
sure, sure, sure.
doubts regarding that.
Yeah, yeah, yeah. What I will do tomorrow is that I promise I'll keep it short to 1 hour, and then we can have another half
Yes,
an
ma'am. We'll
hour
keep it for 1 hour,
for
and we'll for half an hour
whatever
we'll have
doubts
a
there
doubt
are.
session.
Yeah, 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 yeah. Sure, sure, sure. Okay, okay. Thank
Okay.
you. Uh,
Thank you,
shall
ma'am.
I?
Thank you for your
Okay.
time.
Shall I leave right now or yeah?
No, ma'am. No, ma'am. Like if students has any doubt, you can just answer them. The students, you can text your doubts in the chat session so that ma'am can see that
Yeah.
directly to the ma'am. If not, like if you're feeling it shy to show that question to the everyone regarding that, you can just text directly to the ma'am so that ma'am can assist you regarding it.
Yeah. And you can ask me any questions, like even if you have questions regarding career perspectives, or if you want to ask me about IIRs or anything, you can ask me. Okay, there is a question which says which rays are more dominating for study of geoscience and structural mapping below the Earth's surface. Now, when I talk about below the Earth's surface, now you know that this particular no such electromagnetic radiation is going to penetrate the Earth's surface. If you are talking strictly below the Earth's surface, you have to go for geophysical investigations. Like if you're talking about mental, you have to go with geophysical investigations. Now, what you can study from the upper surface is that, like for example, for example, you asked me like structurally from above you can see, okay, there is a mountain, there are ridges, so that is understandable that beneath it you are not going to find a flat lithology, right? You will have a folded structure beneath it. From that you can concur. If you want to know more about it, you go there, you do a GPR study, you do a ground penetrating radar study, or you do electrical resistivity. But to find out about lithologies and structures and everything that is below the Earth's surface, you have to go with geophysical investigations. Okay, how to enter ISRO in remote sensing field? Okay, first of all, if you are a geology student and you have a degree in remote sensing, or you have an MTech in remote sensing with a master's in geology, what you can do is that they give on advertising about scientist positions. There are various centers of ISRO. It's not only one ISRO, that ISRO office in Bangalore. ISRO has many centers. It has space application centers in every region, like in almost all the big cities. In Northeast also we have the Northeastern Space Application Center. Then you have the National Remote Sensing Center in Hyderabad. You have regional remote sensing centers. So in every remote sensing center you have to go to their website. You have to keep on checking if they are giving they have GRF positions. They give advertisements regarding GRF positions, for research positions, project positions. Then they have scientist positions as well. But although for being a scientist, I think you need a PhD degree. With an MTech degree, you can definitely join as a research associate or a GRF associate, whatever the application is about. If you want to join IIRS also, recently there was actually a position of research scientist that they advertised for. I think those seats are right now, they actually got candidates for those seats. But look, you can visit IIRS site all the time. They took lots of GRFs also in IIRS a few days back. So you can go and check their site and see. They are coming up with advertisements. So how geoscience and remote sensing connect each other? Well, as I said, in geosciences you cannot go to each and every place every time and measure. What we do in theoretic, like what have we studied in BSc? We go to field, we see the rocks and surfaces. Just a second, okay, just a second. uh, Yeah. Okay. Am I audible right now?
Yes, ma'am.
Yeah, it was actually Nitish. He thought that the session is over. Yeah, so I was talking about the application of remote sensing in GIS. I hope I cleared your doubt here. I'm saying what remote sensing method is used basically for mineralization study. We use hyperspectral remote sensing. We also use multispectral, but there is something called band ratios. It will take me a lot of time to explain what are band ratios. You can search, and of course, I'll be discussing about it in the 3-week workshop about band ratios as well. But primarily for really good accurate results, you use hyperspectral remote sensing. Okay, Lalit Madhav is asking, okay, he has completed MSc and he wants to do an extra course regarding remote sensing. See, Lalit, since I have studied from IIRS, and if you really thought that today's lecture was insightful and it was good, then it is all thanks to IIRS and the faculty there. And let me tell you, you will in IIRS you don't work with professors, you work with scientists, or they are direct ISRO scientists. So I would like to tell you, if you really want to have a course in remote sensing, go join IIRS. I would really suggest, because their program is very extensive. Even if you do a postgraduate diploma of 10 months, it's a very extensive program. If you're doing MTech, then also it's very good. Yeah, someone is asking, I want to study MTech. So I would say that go join IIRS. You will have a 2-year study, 1 year there will be project work, and it's really good and extensive. Not only about remote sensing and GIS, you'll be also learning programming skills there, which is actually very important in this field. So just go check their website, check all the departments, which one you want to join. If you have more doubts, you can ask me tomorrow as well regarding it. And someone is saying welcome. Okay, thanks. From Somalia also people had listened to our session, so thank you for joining with us today. uh, okay, you want the link of the website? Okay, I'll try to put it tomorrow. You can just go and click IIRS, Dehradun on Google, and you'll get this iirs.gov.in is the name of the website. You can go there and check, all the information is there. Okay, I think questions are done, I believe. Shall we end the session now? Hello, am I audible? Hello, am I audible? Okay. Yeah. So thank you very much for listening to me for such a very long time. Hopefully I did not bore you guys. So thank you very much, and we will meet tomorrow at 5 p.m. sharp. Uh, so till then, bye bye. Good night.